In this section, you will learn analog IC design flow. There are few components in full custom design. Figure above shows the layout design of these components. The components consist of BJT, capacitor, diode, MOS, resistor, and custom design. In full custom design, the designer has full control of circuit structure and performance. It takes a long time to design, but it only applies for analog or RF design circuit. It is also restricted to small circuits or large circuits with repetitive structure, for example, memory. It is not practical for multi-million gate design. Now, let's take a look at full custom design flow.
The figure in this page depicts a flowchart of the full custom IC design process. Let's go through each step in detail. The design process starts by defining the performance specifications, functional requirements, and design constraints for the target IC. Based on the specifications, the analog and digital circuits are designed at the transistor level. This includes the design of individual components like amplifiers, logic gates, memory blocks, etc.
The full custom design flow begins with design specifications. It is important as a designer to identify the design specifications. It determines the performance of the overall chip design. The second step involves schematic design. Designer design the schematic circuit in EDA tools. In this course, you will learn cadence tools. It is one of the popular tools among industry. The third one is simulation. Why is simulation important? It is to validate or verify the schematic that has been designed. In step number 4, we will determine the specification. The results will determine whether the specification has been met.
The design circuits are simulated using electronic design automation (EDA) tools to verify their functionality and performance. The EDA tools that will be used in this course is cadence. This step may involve running multiple iterations of the design. The iteration will not stop until the design specifications are met. The circuit schematics are translated into the physical layout of the IC. This involves placing the transistors and other components, routing the interconnections, and ensuring design rules are met. The layout is checked against the design rules and for any design rule violations using verification tools. Parasitic extraction is also performed to account for the effects of the physical layout. The extracted layout with parasitics is simulated to ensure the design still meets the performance specifications. Additional checks are performed on the layout, such as design rule checking, layout versus schematic verification, and electrical rule checking. The verified layout is used to generate the photomasks required for the IC fabrication process. The IC is fabricated in a semiconductor foundry using the generated masks. This generated mask is called GDS file. This full custom design flow allows for maximum design flexibility and optimization, but it is also more time-consuming and resource-intensive compared to semi-custom or standard cell-based design approaches. The level of customization depends on the specific requirements of the target IC. In this course, the design steps covered up until the schematic design only, which end at pre-layout simulation. This is before a physical layout is drawn. You will learn the physical layout design in other series of this course.